Okay, good morning, everyone. It is time to start. Tom, can you hear me? Can you verify that everything's okay?
Everything is okay.
Good. Okay, so I guess you now have had 2 exercises and also some grading sessions. So before we begin, are there any comments or any feedback, anything that we can improve or anything that you'd like to see different?
Excuse me, can you hear me?
Yes.
I just want to ask you if do we have any exam aid during the exam on Friday?
Do we have any? Can you repeat, please? I didn't get that.
I mean, if we can bring some like cheat sheet or
Yeah. So yeah, it's a good question. However, for the exam, no aids are allowed, which means you can only have your pen and your leggy or like your student ID, like no books, materials, no written aids, nothing.
Okay, thank you.
All right, if there are no more questions, then we'll continue with the lecture. Good. So today we are at this day 3 of the lecture, where you just you're coming off your deadline for the exercise 2. We have lecture, exercise intro, and then you have exercise with the TAs. We have some info on the logistics side. So we have now scheduled what's going to happen on Friday, on the last day, of course. And basically, first thing in the morning that you will do the multiple choice exam, which will be about 45 minutes, like starting at 8 o'clock sharp. So not 8:15, but 8. And the exam is in person. So you have to come to Hauptgebäude or HG, HG at 8 o'clock. And then you write the exam. The room is E3, I believe. And then you have then 1 hour break, such that you can either go back home or find a working space and log into the Zoom call. And then we will have a case study from Robotics, where they will show you how they use ROS on their quadrupedal robot. Then we will have exercise 5 intro, which will be somewhat shorter exercise than the rest. Then you will have time to solve it together with the TAs, and then you have to hand it in the same day. And we expect to be over by 1 o'clock, I hope, at the latest. If you look this carefully, what's missing here is maybe deadline for the exercise 4. And we have decided to, originally was supposed to happen on Friday. However, we have decided to move it 1 day earlier, simply because everything over Zoom, it seems that it takes longer time. And then we will have more time on Friday to do the exam, to do the exercises and the case study. So here is just a summary of what I told you. So the exam takes place on Friday, 5th of March at 8 o'clock sharp, and you have to be there in person. Please be there 10 minutes before, such that you can enter the room, such that we can assign you to your seats, and such that we can then start on time. And also, if you don't want to take the exam, please then deregister from the course by Monday. And we are asking you this simply because we have to come up with a seating schedule, and we need to print name tags, etc., such that you are all far apart from each other, and such that we can comply with the Corona rules. Also, masks are mandatory for the exam. One day before the exam, you will have exercise 4 grading session, which will be then 4th of March, again at 8 o'clock, where TAs will grade you, and then you can spend rest of the day studying for the exam. Are there any questions regarding this new info? All right. It will be also posted on Piazza, just to make sure that everyone gets it. All right. So then today we start with course 3, and we will talk about TF, which is a transformation system, which essentially allows you to reference different coordinate frames that you might have on your robot or in your environment. It's pretty much important for all robots. Then we will talk about Rqt User Interface, which is a set of tools for kind of more convenient analysis and more visualization of different things that are going on in the background. We will briefly talk about robot models or URDFs, which is basically what you pass into Arvis and Gazebo. And we will talk about simulation descriptions, which is something that Gazebo needs in order to simulate your world. So then we start with the TF, with the transformation system. And as I mentioned, so it's just a tool that allows you to keep track of all the coordinate frames over time. So here, if you look on the right-hand side, this PR2 robot, there's many coordinate frames. Like there's a bunch of coordinate frames here in the wheels, in the joints, then there's coordinate frames of the gripper, maybe some coordinate frames here on the head in the sensors. And if you want to do any task, you often have to ask yourself, okay, where is my gripper with respect to my body, maybe? And then this you typically do using TF, where you can query then where is the coordinate frame attached to the gripper. So you can ask all kinds of different questions here, like where is my coordinate frame now? Where was it 5 seconds ago? Where is it relative to the world? Where is it relative to maybe some other frame on the same arm? TF keeps track of all of that for you. It is basically implemented as kind of publisher subscriber node. So there's multiple nodes that are both listening and broadcasting on the same topic. And it is implemented, it basically maintains a tree structure in which it buffers all the information about different coordinate frames. And then at query time, when you ask, okay, give me maybe my coordinate frame of the head at time, I don't know, 1.5, it will traverse the tree, and then it will compute the right thing for you. So TF is distributed, which you can also see here in the image. You can have multiple nodes publishing on the same topic. It doesn't have to be time synced, and the messages on TF can also arrive out of order, which means that you can have maybe one node that publishes on 10 Hertz, and then the other one that maybe publishes on 30 Hertz. One thing that TF is not great for, it's maintaining long histories. So kind of anything longer than 10 seconds will become slow to query, simply because this tree structure will get very large and you will no longer have real-time performance. You can still do this. This should probably be done in a separate node that it's kind of not time critical. Another convenient feature is that it lets you transform points and vectors between coordinate frames. So for example, if you maybe have an IMU attached to your arm and you want to know what is the acceleration, so clearly the IMU will measure in the IMU frame, which is somewhere on the arm. And then if you want to know maybe what is my angular velocity, but in the world with respect to the world frame, you can use TF to transform these vectors. So here is kind of on the right hand side is the visualization of the TF transformation system, and this is the transform tree. And so here you have, for example, if this is your mobile robot, you can see that all the coordinate frames are kind of buffered in this tree-like structure where you always have a parent and a child. And if you look at this text here on the right-hand side, what you can see is that there's many different nodes broadcasting to the TF topic. And you can also see that there is different rates at which they're broadcasting. For example, 10 hertz here, and then also 50 hertz here. You also need to, if you want to work with TF, you need to use a TF buffer, which is just a data structure where this tree is stored. And then when you need a transformation, then the class will basically look up this for you by traversing the tree and compute and spit out the number that you want. This is how TF messages look like. So essentially, you just kind of have geometry message transform, where you store translation and rotation of your child frame with respect to the parent frame, which is this string frame ID, and then you have also header and some like sequence time stamp. So here are some tools that are convenient when you work with TF, and that we will briefly try in the command line. So here, this rosrun TF monitor will basically spit you out information about which frames do you have in your system, which nodes are alive, and you can just simply call it from the command line without the argument. Then if you want to quickly find out now maybe where is your base of the robot with respect to the world frame, you can just run rosrun TF echo. And if you want to visualize all the different frames that are in your system and get like tree structure like this, then you can use rosrun TF view frames. So one thing that I noticed is that actually this function here, rosrun TF view frames, is broken in rosnoetic, which we will see in a minute. And this is not error on your or our side. It's simply that people who wrote the ROS node have messed up. And here on GitHub, there's a pull request to fix this, but it has not been merged yet. So if you try to run this, you will get an error. However, what you can do is you can do rosrun TF2 tools view frames, which will essentially give you the exact same thing. So maybe you're wondering what's TF and what's TF2, which is a very good question. And simply TF2 is a bit newer implementation of TF. They do the exact same functionality and they represent the exact same concepts, except that TF2 is the implementation is better abstracted away. So it should be better from the software engineering point of view. If you have to work with legacy code, often you will find TF, and then you should use TF, same as the rest of the code. And also TF is used in a lot of tutorials, which is why we're also showing it here. However, if you were to implement something from scratch, then we'd recommend using TF2. Okay, so now what I will try to do is kind of run all of these things in my virtual machine. And my virtual machine is a bit slow. Okay. So we're just gonna go into workspace from one of the exercises. And we need to source our workspace. Oops, source setup, right? Setup.bash. Do you see both the terminal and the slides now? Okay, I see many people replying yes in the chat. That's good. Thank you. Okay, so what we will do now is we will just launch our gazebo simulation. And what we can do now, okay, hopefully this starts. Yes, the robot is alive. And now we will open a separate terminal here. And now we will just do run tf monitor. And so you can see that this node here, what it does, it tells me basically all the frames that I have in my system. And it tells me what is kind of the average frame rate and a bunch of other information that they're published on. You can also see here there's something like TF publisher static. So what this means is simply that if you have a static TF publisher, you typically use this for frames that do not change over time. So for example, if you maybe look here at our robot, and if I zoom in, so you can see between this LiDAR sensor and this maybe LiDAR mount here, there are no joints that are actuated. So this sensor always stays on the same distance with respect to this link that it is attached to. So for this case, you would typically use a static TF publisher, which then just publishes a transformation which does not change over time. Okay, so now we can try to do run tf view frames. And what this will do, it will listen to your TF tree for 5 seconds. It will build a tree and store it in a PDF file. However, you can see we're getting here an error simply because this functionality is just broken on Rqt. But what we can do is run tf2 tools view frames, and this essentially, and you can use tab to invoke the autocomplete function. And what you can do now, so you see now this generated these two files, frames.gv and frames.pdf. So now we can quickly preview this PDF file. And now, how can I pan here? No, okay. So here now you can see basically, this is our TF tree. So here we have Odom frame, and then this is the base of the robot. You can see names of the nodes that are publishing this, their average rate. You can see kind of then the structure. So in our case, we have everything attached to the base, and then maybe some of these children go down 2 levels. So this is really convenient if you want to quickly see whether your TF tree is broken, or you maybe have 2 TF trees, or like if something's very wrong with your system. So if you try this TF2 tools, maybe it did not work for you, probably because you don't have it installed. So what you can do is just sudo apt install ros noetic. This would be then TF2 tools. So basically with this command, and then you type your sudo password, And then hopefully you're better at using the keyboard than I am. Nope, still not. Ah, it's because I'm on my virtual machine. Okay. And so here I have already installed it, but this is how you would install it on your machine. Okay. So another thing that you will do in your exercises is this Arvis plugin, which Arvis is just essentially a tool that you can use to visualize. I think it was introduced in lecture 2. Tom introduced it. And you can also use Arvis to visualize both your robot model and your TF3. And here is an example of just how the TF3 looks like in Arvis. So this is kind of like a skeleton of our SMB robot. And here you can see coordinate frames in the joints. This one in the middle is the base link. And then here you have coordinate frames for the sensor and also for the IMU. It's also, if you want to see this whole thing moving around, it's also important to change the fixed frame, which is a frame with respect to which stuff is visualized in Arvis. So, for example, if I put my fixed frame as the base link, then I will see just kind of world rotating and moving around the robot, but the robot will be fixed. Which can be a bit unintuitive. So if you want to see everything from the kind of third person's view, just change the fixed frame to autumn. And here is, so this is then just the robot and all the frames that are attached to it. So I'll quickly show you now. You will, I guess, already do this in the exercises, but we can just quickly try to launch this thing together. So you can quickly start Arvis from your command line. And then if you go here onto this add button, you can find TF3 here. You can click add. And right now it's complaining because my fixed frame is map and I'm not publishing this transform. So I will just change this to Odom. And now you can see, so this is basically then my robot. I will also show you just a bit ahead of time how to add the robot model, which is also something that you will do in your exercises. And okay, so if you get problems like this, it simply means that just the meshes cannot be found. So here I'm getting some exceptions. And they cannot be found because they live in the SMB workspace, which I did not source in this terminal. So hopefully this should fix it. Devil setup bash. Okay. So if we run Arvis again, now it should be able to find all the meshes and stuff. So robot model should be, there we go, robot model. And then we'll also add the TF, and we'll change this frame to Odom. And so now you can see basically the full robot model and the attached coordinate frames. Important thing is to change this parameter robot description to the name of your robot description, which is stored on the ROS parameter server. So if I do maybe, I don't know, robot description 2, now this is not working because there's no parameter with the name robot description 2. So you have to make sure that this name here is the same as the parameter name on the parameter server. Okay. All right, and so here, here is basically the TF transformation system, just the C++ API, and this is how you would then query the TF if you were to look for a transformation, but from within your code. So as mentioned, you have to fill the you have to have a TF buffer, which is just a structure in which TF3 is stored. And then you also have to instantiate this class transform listener, which is basically a class that will then fill the tree inside the TF buffer. What is really important here is that this transform listener, such that this object here does not run out of scope. Simply because if this runs out of scope, then there's nothing that will fill your TF buffer, and your TF buffer will be empty. And then if you look up transformations, you will not find anything. So typically, if you were to work with a class, you should add this. You should add this this class here as a member in your other class. And then to look up transformations, you would simply do TF buffer, and you would call the method lookup transform, and you would give the frame IDs, which are just strings, between which you are looking for a transform, and you would give time at which you would want the transform. I think ROS time Tom will introduce in lecture 4, if I'm not mistaken. But to get the latest transform, you can just use ROS time 0, and this will get you the latest transform. You should not use ROS time now, which is also a function that gives you time at this very moment, simply because it might be that this TF buffer, it might be that the latest transform has not been stored yet. And then what you will do is you will ask the TF, what are the coordinates of my coordinates frame at time t, but this time t will be in the future. And then TF will have to extrapolate in the future, and it will give you an error. So here you can see this is just a snippet of code that basically implements this functionality. So you have to include the proper header when working with TF. You have to instantiate TF buffer and TF listener. Note that this TF listener is basically alive. It's alive during the whole main function, so it only goes out of scope here. Which means that here then we should be able to look up transforms. And then so here we're just looking up some transforms at 10 Hertz, and there's a bit of code around this line here, and this is this try and catch block, which is simply just a C++ mechanism to catch exceptions. And exceptions is something that your program will spit out or throw once things go bad. So usually if you, for example, try to look up a transform here, and maybe you put in the wrong frame name, or maybe you're doing it in the future, this function here will throw an exception. And then this exception will propagate upwards. And if it's not caught by this here catch block, it will crash your program. And this is something that you usually don't want to have. For example, if maybe time is a bit off, you don't want your whole program to crash. So then it's a good idea to put these lookup transforms inside try and catch block, whereas if this now throws an exception, this exception will be caught here in this block. And what will happen then is we will just print out a warning this whole loop will pause for 1 second, and then we will continue with the execution. Without this try and catch block, this exception would then propagate outside of the while loop. Then it would propagate outside of the main, and then the operating system would eventually catch it and it would terminate the program. So then your robot after that would be on its own without any software running on it. Okay, are there any questions related to TF? Good. Then we'll continue with the Rqt User Interface. So Rqt is just kind of ROS adapted Qt, which is a tool for visualizing different stuff. And mainly typically stuff that you might want to visualize are like some plots. How does maybe, I don't know, IMU measurement evolve over time? You can also build your own GUIs with some plugins. You can build your own plugins. You can basically drag and drop them into this window, and then you can maybe add some buttons such that you can control your robot. There's also a bunch of existing plugins that you can use. Like maybe this, the Rqt Console or Rqt Multi-Plot. And it's relatively simple to write your own plugins. There's already existing plugins if you're working with some sensors. For example, if you have a camera, you can just run run Rqt image view, or you can drag and drop the camera, this image view plugin inside this kind of main Rqt window, and then you can visualize the image stream from the robot, which is fairly convenient if you want to quickly debug something, like maybe see that your camera is not completely blinded, that there's pixels that are alive, etc. Like you could also, for example, do this from the terminal. You could do ROS topic echo and then just name of the topic that this image is being published. So in this case, this would be Kinect head RGB image color. However, what this would do is it would just print you the matrix. Assuming that you have grayscale image, it would just print you a bunch of floats in the terminal, which is not very human readable. So then this is a convenient tool to quickly see what's going on in your system. Another thing that we will quickly try is this Rqt Multi-Plot, which is very useful if you have to visualize maybe how stuff evolves over time. So for example, here, I think this is, yes, this is a plot of for a quadrupedal robot, and these are joint angles in one leg. And then you can see here basically the reference, the desired joint position, and then the actual track position. And then you can also pause or play this plot, and you can store different configurations, save them for later. You can export everything. And it's really nice if you have to, for example, tune maybe a controller, or if you want to verify that maybe all joint positions or torques are within the limits. It's very similar to MATLAB, essentially. Another thing that it's useful is this Rqt Graph, where you can then quickly visualize all the nodes, which are these ellipses here. And you can also visualize all the topics that are active in your system together with the interconnections between them. So here I can see that node joint state publisher is publishing on the topic, it's publishing the topic joint states, and then robot state publisher and move group, these two nodes are subscribed to this topic. If you remember your lecture 1, you could also basically build this graph on your own using command line tools. So you could do ROS topic info and ROS node info, and you would eventually come to the same structure. This is just maybe a quicker and not more convenient way to visualize it. Command line tools are also useful, and it is a good idea to know them, simply because often when you are working with a robot, you don't have a screen and you're just connected over SSH maybe, and sometimes over poor connection. So then if you want to debug stuff that's running directly on the robot, command line tools are very useful to know. Another thing is this Rqt Console, which what it does, it gathers all the information from multiple processes, and then it displays them here conveniently in this GUI. So if you have maybe multiple terminals open, it can be a bit hard. And now all of them are showing some information. There's like a bunch of warnings or infos or whatever coming up. It can be, and everything is in real time, it can be a bit hard to process and a bit overwhelming. So then you can also use this tool where you can basically, everything is stored and displayed in a bit more user-friendly way. You can also set up some exclude rules and maybe tell, hey, just show me only the messages coming from this node. And then it's a bit easier. It's a bit easier to find the information that you're looking for. You can also change the logging level of the ROS nodes if you start the Rqt logger. So you can simply select the node that you want to configure the logging level for, and then you could change, for example, display me only output that is higher level than info, including info. So this means here we will display all the info output and warnings, errors, and fatal errors. So then the lowest level is debug. If you select debug, basically all of these types of messages will be included. If you select warning, then only warning, error, and fatal errors will be included. Okay, so maybe we can quickly now try to run some of these things. Okay, is my simulation still running? Yes. So one thing I realized I forgot is I forgot to show you TF echo, I believe, which is just a transform, which is just lookup transform between two frames. So we can quickly now do this for the SMB here. We can just say ROS run TF echo, and then we have to put names of the frames. So for example, odom to base link. And now this tells me basically that my robot is in the origin of the odom frame, but I can quickly try to move it around a bit. Teleop twist keyboard, teleop twist keyboard. Okay, so now I have my keyboard node running, and I'm just gonna tell the robot to go a bit straight and move in the circle, which the robot is now doing. And you can see now in this terminal here that basically rotation of the robot changes and the position as well. And if I tell the robot just to go straight, so now you can see that only kind of the position changes and that this yawing angle stays constant, and the robot is just going straight in a straight line. Okay, so then let's try to fire up the Rqt. So you can simply do Rqt. And here I already have the multi-plot, Rqt Multi-Plot open. Maybe I can make this full screen because it's a bit cluttered. Does that work better? Maybe. Okay, so now let's say we want to maybe visualize some IMU data from our SMB, which at the moment is just standing still here in the simulation. Maybe I can navigate to it. Yes, so nothing is really going on. And so I can quickly here, so here you can add new configurations, you can load old configurations, or we can just, so we have here already one plot. So I will try to configure it, and I will say maybe, I don't know, let's call this angular velocity plot. And then we can add a new curve here. And now we have to find the right topic that this IMU data is being published on. So we can try to find here just by topic name, we can say IMU0, and then it auto-fills the correct message type. And now you just have to select which field. And let's say we want to visualize Z angular velocity over time. So I can put time on my x-axis. What I can just do is I can look it up from the header and put the timestamp. And then on the y-axis, I will put angular velocity. And let's say I will put just the Z one because it's the easiest thing to test. And we can maybe make the pen a bit wider. And I can click OK. So now nothing is going on. Simply because I also did not really name this. So let's quickly fix this. Omega X. So this just means that we're plotting, omega Z. Z component of the angular velocity. So now nothing is happening because I have to click play. And now you can see that my angular velocity is basically almost zero, simply because the robot is standing still. And then if we tell it to move around, which is what it's doing now, so now it's just rotating. Now you can see that this angular velocity has changed to something, and it's a bit oscillating, which is simply because of the way the skid steer plugin inside Gazebo it's implemented. So this is quite useful if you now have to see that joint limits are within the range, or that maybe if you're plotting some positions and references, see that robot indeed reaches the desired position, etc. It's especially useful for like tuning PID controllers. And then you can pause your plot. I think this will clear it. Then you can also start all over again. And like notice how the time scales here. And then if I also just pause my robot, if I tell it to stop, which now it has done, this angular velocity then just goes back to 0. So now we can close all of this, close the node, and then we close the TF. So this Rqt Multi-Plot, I believe you will have to do this in one of the exercises. And we can go back to the lecture. Maybe just one quick more thing to show you. So if I run everything again, and hopefully my virtual machine's not too slow. Doesn't look too great. No. Okay, so it just doesn't like full screen, it seems. Okay, let's try now. If you just load Rqt, and then you can here drag and drop different plugins. So for example, if I now want to visualize my image stream, I would do plugins, and then I would say image view. And now I could choose some topic, but now I don't have a camera in the system, so there's nothing being published. Or you could also see, for example, the TF tree that we saw in the PDF. You could also just say plugin, visualize me TF3, and then you can see the same information here. Okay. Present. All right. So another thing that you will work with are the robot models, or URDFs, which stand for Unified Robot Description Model. And this is how you tell basically your Arvis and Gazebo how your robot looks like how does it look visually, what are the properties, maybe like dynamic properties or collision properties, etc. So it's just an XML format, and it contains kinematic and dynamic description, which are like masses, moments of inertia, and maybe some other properties like friction parameters in the joints. It contains visual representation, and it contains collision model. So here on the right-hand side, if I get my pointer, so here you just have a visual model of a Husky robot, which was used before. And then you can see how this visual mesh is really nice to look at and very detailed. However, you don't want to use this for collision detection because these meshes can be arbitrary complex. They're just basically big sets of triangles, and then detecting collisions on a mesh is very expensive, which is why for your simulation, you would typically use primitives. So here you can see the same robot, but here it's composed just of like primitive shapes like cylinders for the wheels, and then these kind of 3D rectangles for bumpers and main body, and also for the sensor. So these collision bodies, at every time step, basically Gazebo simulator computes which one of these bodies is in contact with the ground, and then if it detects that it's in contact, it computes corresponding forces, and it then simulates how the robot would interact with the real world. This URDF generation can be also scripted with this Xacro scripts, which is something that you will not do very often because rarely you set up the whole new robot model from scratch. But just so that if you see this, it's essentially a tool for generating URDFs for really complex systems. So it allows you to define different macros and different includes, and then maybe if you want to have your Husky robot not with this sensor, but maybe with a camera, you can just simply pass some arguments in there, and then this Xacro will parse correctly these arguments, and then it will spawn the right model, or it will generate a URDF description for a model with or without the sensor. I see some questions here. Can you export a CAD model to URDF Xacro directly? I believe you can. Some tools will support this, but usually it does not work very well. Visual representation you can do for sure. Collision models, often you have to build from scratch. So a little bit more about this URDF. Basically, your robot is a set of link elements and joint elements, and then joints connect the links together, such as shown here in this image, where you have 4 links, and then between each pair of links, there's a joint. And then inside the URDF, you put robot name, robot, and then you put links. And now where these 3 dots are between these sets of link tags, you would put some link properties, and then same thing you would do here for the joint properties. And so here, for example, this is link with a name, link name, which is very imaginative from our side. And here you can define the visual property, which is just you can send some meshes in this collada format, and then this will be used just to render your robot. And then, for example, for collision, you can say, okay, this collision body is just like a cylinder, which maybe could be your wheel or something. And then you can also define inertial properties. So like what is mass of that link? And then here you would define the whole inertial matrix 3 by 3. You can also do the same thing for joints, where you tell what is the name of the joint, and you can say which type is the joint, maybe. So this one is revolute, but it could also be prismatic or even spherical, or I think there's also some other types that exist, which you can look up here under this link. And then here you can limit the effort, which would just be like the joint torque or joint force in case of a prismatic joint. You can set the limits for position. You can also set some friction parameters, etc. And then here you specify what is the parent link and what is the child link. So for example, for joint 1, parent link is link 1 and child link is link 2. And here then you just specify position or like pose of your joint frame inside the parent link frame. So how do you then use this robot models in ROS? This robot description URDF is stored, as I mentioned, while we were visualizing it together in the Arvis. This is typically stored on the parameter server, and usually the name is robot description, although you can put an arbitrary name here. And usually then this kind of just parsed URDF is just a giant string, which is not human readable. And then how do you load it is usually you load it from your launch file with this xacro command, and then you find your URDF, you pass it to the xacro script, and you can also parse some arguments here, which will then generate the correct URDF. And this tag parameter here just means load this onto the parameter server. So this is how we did it for the SMB code. If you dig a bit inside the SMB common repository, and if you dig inside the SMB gazebo package, so there you will find that the top level launch file eventually at the lowest level includes something like this command. And then if you want to just maybe use this description within another launch file, again, somewhere not on the lowest level, but on the higher level, you will find that we just include this find SMB description, and then this load launch file, which is then the launch file that just calls the xacro parser and that uploads stuff on the parameter server. And then here you just pass the arguments, same as you do for regular launch file. And then once this is on the server, this is how then Arvis knows where to find all the collision bodies, where to find all the meshes, and the robot description. There's also something that it's called Sdfs, which is simulation description format, which is something that Gazebo uses. So each time you pass a URDF for Gazebo, Gazebo internally converts it to an Sdf, and then it generalizes simulation for you. So Sdf is a bit more general than URDF, in the sense that it could also simulate some maybe sensor plugins, so some sensors, so you can define like maybe your laser sensor, and then you can define the corresponding plugin, and then you can mount it to your robot and kind of stream point clouds or laser scans on a ROS topic. It also, so you can add objects like static or dynamic. So for example, here, this house might be a static object, which means that it cannot move. However, this car is probably a dynamic object. You can add multiple robots, and you can also add, you can play with your environment. So you can add maybe different gravity or different lighting settings, etc. So for the exercises, these kind of .world files is basically, those are Sdfs. And typically you will not have anything as complex as here. For us, they're just very simple. So this basically brings me to the end of this lecture. And then before we give you an introduction to the exercise, are there any questions about this? Okay, so I guess no, which means either that I'm a great lecturer or that you're all still asleep. Okay, so then let's try to run the exercise and see what to look for. And let's hope that my virtual machine is in a better mood than it was a few minutes ago. So I can maybe just kill this simulation and let's find the exercise. Here. Okay. So everything should be uploaded here online, and this is definitely the correct exercise. Okay, so first thing that you could do, we noticed that some of you had problems that basically Odom frame was not popping up and the whole simulation was just very slow. So we cannot unfortunately help you with that. However, what we did is we just basically disabled the TF publisher inside the Gazebo plugin, which as far as I've seen would not load for some of you correctly, or it would have to be manually loaded. There was a question related to this on Piazza. So I would recommend you to then use this SMB Common version 2, which is the same simulation. It just has, we changed 2 parameters such that we disable the TF publisher from Gazebo, and now the transformation Odom to base is coming only from the EKF localization node. So it's the same procedure as in exercise 1. You can just download this here from the course website and then compile it just with Catkin. Okay, so then you will have to download this single pillar world for Gazebo. And then the goal of the exercise is to have the SMB robot just hit that pillar. So again, on the course website, there's this single pillar world, and then you can adapt your high-level controller from the last lecture. So how this looks like, we will run it later, but essentially there's like a giant cylinder inside Gazebo. And then at the beginning, the robot is somewhere here, so it's quite far from it, and it has to drive a bit to reach it and then to hit it. And then the goal is to do this automatically. So here are some images that will help you hopefully with coordinate frames. So this is top level of the SMB. And then you can see, so red axis is X, Y axis is this green axis, and then Z is pointing outside of the paper. So this is the blue axis. So you can remember this is RGB and XYZ. It's fairly easy. So then this is how this is the base link coordinate frame of the SMB, and then the sensor has the same coordinate frame as this. So they are aligned, just offsetted in Z coordinate. And then this laser scan message that is being published on the scan topic. So it looks, this is kind of the schematic of the scan. So you have angle minimum and angle maximum, which is just the angle at which the laser starts firing. And then it measures a bunch of these ranges. And then this goes counterclockwise and it finishes here at angle maximum. So for our case, these angle minimum or angle maximum are defined to be minus 90 and 90 degrees. So there's essentially the robot is blind in the back. You can't see anything in the back. And how the ranges start, so basically ranges is an array inside the message, and then ranges, the first element is this array here, and then and they're just incremented by this angle increment. So for example, third element of this array would be array maybe pointing somewhere here, which is basically 2 angle increments then away from the first ray. So you will have to basically modify your publisher and implement this simple P controller. And then one thing to note here is you have to basically ensure that you can see this pillar in your scan. And you can do this by setting these 2 parameters, laser scan min height and laser scan max height, to these respective values. So the reason for doing this is, I guess, for some of you who looked at the bonus exercise, what we actually have on, so I will now try to run the exercise and then maybe show you this in Arvis. So we have ROS launch SMB high-level controller. Okay, let's see. Okay, so here now you can see SMB has just been spawned and it's like slowly driving towards the pillar. So what we actually have for this exercise is not the 2D laser. We have a 3D laser, which you can see some of you who solved the bonus exercises, I think you had to visualize basically this 3D point cloud scan. And then we just use a separate node to convert this into the 2D laser scan. And this is then why you have to set all of these parameters. And then you can see here in Arvis, basically for the exercise, you look at this scan, which are these orange dots here. And then you have to compute what is the position of the pillar, which is marked kind of middle is approximately where this green marker is. Maybe zoom in so you can see better. This 3D point cloud you don't have to worry about. So this is all that you're working with. And then by finding these points, you can compute where the pillar is, and then you can drive the SMB towards it. So you can, since this is just an empty world with kind of nothing else around other than this pillar, the only thing apart from the infinity range in your scan should just be this pillar. So then it's easy to see where to drive. You also might have to play a bit with the P gain inside your controller. So this is why it's important to make it, to load it as a parameter, which I believe is what exercise asks you to. And then often if you see that your SMB is maybe driving the wrong direction or turning the wrong direction, the easiest thing to try is you can just flip the sign of your gain. And then you should be able to drive to the pillar. And then the last tasks are to visualize stuff in Arvis, which we have seen how to do during the lecture. And you also have to publish this visualization marker, which here in my simulation is just this green ball here. And maybe one thing to pay attention here is if you can just follow the documentation and like pick your favorite marker when you're building this message. One thing that is important, so these are all the parameters for the marker that you can use. And most important thing here is this marker color, which is RGB, and this A parameter is just the transparency or opacity, depending on how you look at it. And by default, this is 0, which means opacity is 0 or transparency is 100%, which means that you won't see anything. So you have to set this to 1 if you actually want to see your marker in the Arvis. Okay. And then this is it. I guess the TAs should be ready. And if there are questions, please ask them. Otherwise, you're free to go to your exercise rooms. Okay, there's no questions, so I guess I will then end this lecture. Thanks for attending, and good luck with your third exercise.